Hi students, good evening. Welcome to this video session. I remain Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall complete the remaining questions on your Module 2 homework assignment. So this is part 3 of it. And these remaining questions, questions 10 and 11, deals with even and odd proofs. So I will try as much as possible to do similar question, not the exact question. So if you listen to me, then you would know how to do it. Okay, even if I don't specifically do it. But if you listen to the way I explain it, then you should know. When you're asked to prove or disprove something, you want to first of all check whether the statement is true or false. If you see any example whereby it is false, then just cite that example. Okay, just cite that example, that case whereby it is false, and then you can stop. But if not, if you try all the examples and it is true, then you try to prove it. Let us first of all let's define an even and odd integer. Okay, what is an even integer? Meanwhile, what is an integer first? An integer is a whole number or the opposite. An integer includes 0, then whole number or the opposite of the whole number. Okay? An integer. Integers include, when we talk about integers, we talk about 0, then we have a whole number, and then the opposite of the whole number. Opposite of the whole number. So, when we talk of integer 3, -3, -7, 25, 12, 0, they are all integers. And we say that integer is, we represent it by z. We represent it by z. Z is the set of integers. Okay? Z. Sometimes we just write z like this. Just z. It means a set of integers. If we have z plus, this is the set of positive integers. If we have z subscript minus, this is the set of negative integers. Now 0 is not a positive integer and it is not a negative integer. 0 separates the positive integers from the negative integers. Okay. So when they say non-negative integers, okay, so or sometimes we say positive integers. When we say positive integers, it does not include 0. Okay, it includes just the positive integers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When we say non-negative integers, then it includes 0 and the positive integers. Okay, when we talk of even integer, it could be positive even or negative even. Okay, it could be 4, it could be 6, it could be 8, it could be -4, it could be -6, it could be -8. But when we say just even integer, it could be positive even integer, or it could be negative even integer. If we say odd integer, it could be positive odd integer, or it could be negative odd integer. Okay. When we say positive odd integer, it could be 3, it could be -3, it could be 7, it could be -7, it could be 11, it could be -11. Okay. So note that. Now, of course, 0 is not positive, it's not negative. Okay. So even integer. How do we define even integer? An even integer, let's say P, let's call it P, is equal to 2C, where C is an element of the integers. Okay? This is the definition of an even integer. Even integer, say P. Let's say P is an even integer. Is 2 times any integer. 2 times any integer. Let's check it out. 2 times 1, 2. 2 times 2, 4. 2 times 3, 6. 2 times 4, 8. 2 times 5, 10. So, you see that all those 2 times will give you positive, will give you even integer. All of them. Okay? Even if you come to 2 times -1 is -2, that is still a negative even integer. 2 times -2 is -4. 2 times -3 is -6. So those are even integers. This is the definition of an even integer. 2 times any integer at all will give you an even integer. Okay? 2 times any integer. So an even integer is defined as the product of 2 and any integer. That gives you an even integer. That is the definition. Okay? C could be anything. C could be 101. 2 times 101 is 202. 202 is even. Okay? 2 times 100 is 200. 200 is even. 2 times 17 is 34. 34 is even. So 2 times any integer will give you an even integer. Just know that. Okay? Now, let's look at odd integer. Odd integer. Odd integer, say Q. Say Q. So Q is 2C plus 1. Okay? Where C is an element of the integers. So the definition of an odd integer is 2 times anything plus 1. Okay? 2 times 1, 2 plus 1, 3. 3 is odd. 2 times 2, 4 plus 1, 5. 5 is odd. 2 times 3, 6 plus 1, 7. 7 is odd. Okay? That is the definition of an odd integer. The same applies with negative odd. 2 times -1 is -2. Plus 1 is -1. -1 is odd. 2 times -2 is -4. Plus 1 is -3. -3 is odd. It's just a negative odd integer. Okay, 2 times -3 is -6. -6 plus 1 is -5. -5 is odd. So, odd integer is 2 times any integer plus 1. That gives you an odd integer. So, these are the 2 main definitions you need to know. Okay, so let's say first one. Let's say they prove or disprove. Prove or disprove that the sum of 2 odd integers is even. Prove or disprove that the sum of 2 odd integers is even. Just this is an example. Okay, let's see whether the first thing you do is see whether this statement is true or false. Okay, so let's try with examples. Try with some examples. Try with some examples. Okay, and it did not say 2 positive odd or 2 negative odd. It just says 2 odd integers. Prove that the sum will give you even. And that will work. Okay, but just for simplicity, let us just do 2 positive odd. Okay, 1 plus 3 is 4. Okay, 3 plus 7 is 10. is even, this is even. This is odd, this is odd. The sum gives you 10. Okay? 5 plus 17 is 22. Odd, and even. So you ask yourself, is there any case at all whereby you add two odd integers and it does not give you even number, even integer? And I cannot think of the case. Okay. So this is true. Therefore, you have to prove it. Okay? Therefore, you have to prove it. Now, let us now prove it. Okay? Let's now prove it. Proof. So, we say, let the odd integers be x and y. Let the odd integers be x and y. Okay? So let's say from the definition of odd integer, x is 2c plus 1, y is 2d plus 1. Where c and d are integers. Where c and d are integers. Let me write this integer like this, okay? My z. I can, sometimes we write it like this so that it doesn't look like 2. So it doesn't matter if you, okay? So if you see me writing, just know it's still integers. So let the two integers be x and y. X is 2c plus d, y is 2d plus, x is 2c plus 1, y is 2d plus 1. Because this is our definition of odd integers. So let's just say that this is this. Okay? Now let us add both of them and see what we have. So we now continue with the proof. So x plus y will give us that this is 2c plus 1 plus 2d plus 1. Remember, the sum of two odd is even. Okay. So this means that this will be 2c plus 2d plus 1. I mean plus 2. Right? 2c plus 2d plus 2. And let's factor out. Factor by GCF. Okay? Factor by GCF. So this means 2c plus d plus 1. So as you can see here, c is an integer, d is an integer. So if you add the two integers plus 1, it still gives you an integer. Okay? So let c plus d plus 1 be something like k. So k is also an integer. K is also an integer. Okay? So this now means 2k. 2k. And remember 2 times this is even. So this is even. It's even. Proved. We've proved it right away. That's it. That's how you prove it. Okay? 2 times k will now give you the definition of an even integer. 2 times any integer at all is even. Okay? Now let's do the next one, question 2. Let's do another example. Prove or disprove that the product of two odd integers is 3 times 5. Okay. Odd is odd. Prove or disprove that the product of two odd integers is odd. Question 2. Okay, so just try with examples. And let us just use positive example. Let's use positive odd. I mean, this could also work with negative odd, but let's use positive odd. Okay? So if we have 3 times 5 is 15. 15 is odd. 7 times 7 is 49. This is odd. Okay? 11 times 3 is 33. This is odd. So, but if you can think of any example whereby you multiply 2 odd and it gives you even, then you have disproved this right away with that example. Otherwise, this is true, so you have to prove it. You prove it. Okay, now let's prove it. Proof, and let the 2 odd integers be. Let the 2 odd integers be x and y. So let's say x is 2c plus 1. That is the definition of odd integer. Okay, definition of odd integer. Definition of odd. Y is 2d plus 1. Definition of odd. Definition of odd. Okay. So now the product, let's now multiply both of them. X times y. X times y. Okay? So this will give us 2c plus 1 times 2d plus 1. Right? And then we can FOIL this. We can FOIL it. FOIL. This will give us 4cd plus 4cd plus 2c plus 2d plus 1. Right? 4cd plus 2c plus 2d plus 1. So this will give us this will now give us let me write it here, 4cd plus 2c plus 2d plus 1. Let's try to make sure, you know, we need to get odd. And this is the definition of odd. So we can come here and look at this right here and factor. We can factor by GCF here. So this gives us 2cd plus, remember, let me write here where C and D are elements of the integers, element of the set of integers, set of integers in C. Okay? So this will be 2cd plus C plus D, then plus 1. Okay? Now, because C and D are elements of the set of integers, these also 2cd plus C plus D will not give you fraction. It's not going to give you fraction. It's also element of the integer also. Okay, because C and D. If you multiply C times D, provided that they are integers, you multiply them by 2 and then add them, get the sum. Okay, it will still give you integer. It's not going to give you decimal. It's not going to give you fraction. So they will still give you integer. So therefore this, if you like to call this P, that's fine. I'm just doing several ways. Okay, I know I used let that be K in number 1, but you mustn't do that. Okay, you can also write this, because these are element of the set of integers, 2CD plus C plus D will also give you are also integers. So this now, you can say let 2CD plus C plus D be K. So this will now be from here, this will now be 2K plus 1. And this is odd. Okay? Definition of odd. Definition of odd. Okay? Do you understand this? Alright? Let's do another one. Number 3. Number 3, prove or disprove, prove or disprove that if n squared is odd, then n is odd. Prove or disprove that if n squared is odd, n is odd. Okay? The first thing we do, as usual, is to try some examples. See whether we can find an example that will counteract the case. Okay? So, let's say, try some examples. Try some examples. If you have 9 is odd, right? 9 is 3 squared. That means 3 squared is odd. Therefore, 3 is odd. Okay? 3 squared is odd, 3 is odd. 25, 5 squared. 5 squared is odd. Therefore, 5 is odd. So, do you have any case at all whereby you square an integer, the result is odd, but that integer is even? Is it possible to have any square of, is it possible to have the square of an even integer to give you odd? Is it possible? Not that I can think of. Okay, 2 squared is 4. 4 squared is 16. 6 squared is 36. 8 squared is 64. They are all given, excuse me. So they are all even. Okay, so this is true. You see that this is true. That if the square is odd, if the square of that integer is odd, then that integer is odd. So this is true. We say that this statement is true. And for some statements, you can prove it directly, okay, like we did in number 1 and 2. For some statements, you can also prove it by contraposition, okay, by writing the contrapositive statement. We have done logic and truth tables. You look at this is a conditional statement. It's a conditional statement. If n squared is odd, then n is odd. Okay? So the contrapositive statement would be, if n is not odd, then n squared is not odd. And if it is not odd, it is even. So let us try to prove this by contraposition. So contraposition, or you can say contrapositive statement. Contrapositive statement. Okay. So this will be if n is even, then n squared is even. Okay? So let's see. Some of these statements, you prove it by contraposition. So n is even. The definition of even integer is n equal to 2c. Okay, where c is an element of the set of integers. So square both sides. N squared will be 2c all squared, right? And that will give us 4c squared. 4c squared. And that will give us, we want to make it look like that, 2 times 2c squared. 2 times 2c squared. Now, because c is an element of the set of integers, c squared is also an element of the set of integers. If you square any integer, it gives you an integer. Okay? And also, 2c squared is also an element of the set of integers. If you multiply any integer by 2, it still gives you an integer. So, we can just say, let 2c squared be k. Okay? So we now say, let 2c squared be k. Okay? So this here will now give us 2k, and that is even by the definition. Okay, this will now give us 2k. So if this works the contrapositive way, that means the conditional is true. Remember, the contrapositive statement and the conditional statement are equivalent, logically equivalent. Okay, if you view the videos we did on logic and truth tables, we say that the conditional statement and the contrapositive statement are logically equivalent. Okay, so I hope it makes some meaning here. Okay, let's now go to your questions. Question 10. Prove or disprove that if the product of two numbers in natural, and that n means set of natural numbers. Natural numbers. This is a set. Z is a set of integers. N is a set of natural numbers or counting numbers. Okay. So you could call these positive integers. Prove that if the product of two numbers in a set of natural numbers is even, then at least one of them must be even. Okay, so you try with some examples. Product 4 is 2 times 2, 6 is 2 times 3, 8 is 2 times 4, 10 is 2 times 5, 12 is 2 times 6, 24 is 4 times 6. Okay, so at least all these even natural numbers, when you break them into two products, one of them is even. So it tells you that yes, that the statement is true. So try to prove it, okay? And my hint will be prove it by contraposition. That's the hint I will give you. I don't want to do the exact question, but prove it by contraposition. Now, question 11. It says, prove or disprove that if the sum of two numbers in the set of natural numbers is even, if the sum is even, then at least one must be even. Okay, so you try that. If the sum is even, then one must be even. So 4 is 2 plus 2, but 4 is also 3 plus 1. 6 is 3 plus 3, even though 6 is 2 plus 4. So you see, 8 could also be 7 plus 1. So figure it out yourself. Okay. Like I said, test with some examples. If it is true, prove it. If it is not true, use that example and counter it, that the statement is false. Okay? Thank you so much for listening. If you have any questions, please ask. And you have a good evening.